Next on our list is TD. TD is being two letters, the letter T and the letter D, and that's temperature difference. But really, I have my students remember it like this: two different. It's two different things being compared. For example, our saturated, aka refrigerant temperature, versus the temperature of the air coming in. TD, two different. Refrigerant versus air. We also have an outdoor TD, meaning the difference between the refrigerant condensing temperature and the temperature of the air coming into it. It's a very important number, two different. With our water-cooled system, or water-cooled condenser, we also have a TD, the temperature of our saturated, PSIG converted temperature, versus the temperature of the water. It's going to be a very important number. As glycol systems, we also have a TD, two different numbers, the difference between the evaporator temperature and the temperature of the glycol. So here's going to be the temperature of the refrigerant versus the air coming into it. Temperature of the refrigerant versus the air coming into it. Temperature of the refrigerant versus the air coming into it. Temperature of the refrigerant versus the air coming into it. Very, very important number. Don't get the two mixed up. TD and delta T are two different things. TD, two different. Now, the TD is very important because think about our evaporator. Our evaporator temperature, or the temperature we're boiling refrigerant at, should be lower than the air temperature. So heat will leave the warmer air and go to the cooler refrigerant. Two different temperatures. Outside, our saturated temperature will be higher than the air temperature. So the heat will leave the refrigerant and go to the cooler air. And this goes into many things. You've heard of a creamery that uses a cold stone. Well, we have an evaporator under that stone, or someone's glycol, and we take the heat out of the stone. So there's going to be a temperature of the refrigerant versus a stone. And then as you're working the ice cream on it, the heat leaves the ice cream and goes to the colder or less heated stone. So about heat transfer. So TD is going to be a very important number. Especially in residential, we're going to be looking at TD for the condenser, but there's also, when we get into refrigeration, TD is a very important number, especially when we're looking into walk-in coolers and walk-in freezers. But next, condenser TD. Condenser TD, two different numbers. PSIG converted to temperature versus the temperature of the air entering the condensing unit. If you want to know which way air is entering, put a piece of paper up to it. When it sucks up to it, that's air entering. So the difference in those two different things, refrigerant temperature versus air temperature. PSIG converted temperature to air temperature. It's condenser TD, two different materials. Now there's other words that this is called. This is also called saturated temperature rise. The saturated PSIG converted temperature has risen X number of degrees over the temperature of the air to allow heat transfer. So saturated temperature rise is another word for it. It's always been TD. Now there's also CTOA, which stands for condensing temperature, PSIG converted temperature, over ambient, the temperature of the air coming into it. CTOA, condensing temperature over ambient, saturated temperature rise, or just simply condenser TD, it all means the same thing. PSIG converted to a saturated temperature. That number should be higher than the temperature of the air coming into it. So the next question is, what should that be? Let's find out what it should be. Here I've designed a quick reference guide. So all these mean the same thing. We get our PSIG, convert it to a saturated temperature. So liquid saturated temperature minus the air entering the condenser, or also called ambient, equals TD, condenser saturated temperature rise. That's how we find it. We need to know what type of system. If it's a refrigeration system, they're typically like 25 to 35 degrees over ambient. Now, old systems, old AC systems were like 8 SEER. These are like in the mid 80s and earlier. They were usually like 8 SEER, and our target, what we were looking for, was 25 to 35 degrees warmer than the air temperature. And people usually just said 30 to round it off. So you talk about refrigeration guys, like, well, you should have a 30 degree saturated temperature rise. The refrigerant temperature should be 30 degrees higher than the air temperature. That's on refrigeration, but also these real old systems that don't really matter anymore because they're pretty much gone. Then, next we need to know the SEER. So here's 9 to 10 SEER. These were mandated in 1987. So if the unit's 1987 or newer, it's going to most likely be a 10 SEER. Well, here they started making systems more energy efficient. So here we end up with things like, hey, let's make more surface area. Let's make the condensing coil transfer heat better, and we won't need the temperature to be as high. So now they had a target of 20 to 30 degrees higher than ambient. Then we had 11 to 12 SEER, anything over that, and there's all kinds of options. You can look up the manufacturer number of the system to find out the SEER rating, but they were like 15 to 25 degrees above the ambient temperature. So as we bring that saturated temperature down, that's less pressure we need to work with, and they offset that by a larger condensing coil that transferred heat better. Second law of thermodynamics. They also used more airflow. Now we end up with 13 SEER and above. This was mandated in 2006. Also 14 SEER is mandated in 2015. So if you have one of these newer systems, our condensing temperature would be 10 to 20 degrees warmer than the air temperature. That was the range we're looking for. Now as systems get newer and newer, we're actually having some that are like 10 to 15 and even 5 to 10. It's getting crazy how close they're getting the condensing temperature to the ambient temperature. This is just a guide. If you really want to know the number, contact the manufacturer. They have all kinds of data for this. But this gives us a range that we're looking for. If our saturated temperature rise is too high, so let's say that we have this unit right here, should be between 10 and 20, and we end up like a 30-degree saturated temperature rise, well, we know that we're too high. So we can look for a dirty condensing coil, discharged air recycling. In other words, the air from the condenser is going back over itself. Maybe there's a carport, a tree, something that's causing the air to recirculate. We could have non-condensables. We could have our air blocked, so it's dirty, or maybe a bush is next to it, or somebody built a fence next to it. Refrigerant impurities, non-condensables can give you the same reading. Overcharged, too much refrigerant. So if you have superheat and subcooling, both of those say you're overcharged. You look at this, this also says you're overcharged. Well, there you go. You could have a bad fan blade alignment. So the air in the fan is not moving like it should. Maybe somebody put the blade too low or the blade too high. We're not moving the right amount of air. The fan speed too low. Somebody maybe have put a motor in that's the low RPMs, or they put it in the wrong speed. Or you could have a refrigerant restriction, maybe a clogged up filter dryer or a blockage in the condensing coil, and that's causing this to be too high. Now, if we end up with a low saturated temperature rise, let's say we want 10 to 20 and we only have, say, 4 or 5, we could have a wet coil. Say it just rains. You get through washing the condensing coil. These are things that can cause that. Too windy at the coil. I've seen this on rooftop units. There's a whole lot of wind up there. It's cooling that refrigerant off too fast. The fan's too fast, so they put too fast of a fan speed in there. The wrong fan blade, so it's moving too much air. The outdoor temperature is too low, so maybe they need a low ambient kit. Maybe it's freezing outside or one of those conditions. It could be low in refrigerant, undercharged, has a leak, find the leak. Metering device is oversized. Maybe they put too big of an orifice in there. Or TXV stuck open, or that sensing bulb is loose on it. All of those could cause our saturated temperature rise to be too low. So it's a quick little guide. We want to check the condition of the coil, look for dirt, hail damage, or other damage. Look for corrosion, especially where a dog pees on this. That's a big issue. Or if you're by the sea, corrosion's a big issue. And clearance for airflow from the sides and above. So often that's overlooked. They put too much stuff next to this condensing unit. It can't breathe, can't get enough air. So that is your CTOA, saturated temperature rise, or simply condenser TD. So here we're going to take a look at our condenser TD. Our saturated temperature is 98.5. Let's round that up to 99. That's our saturated temperature. Our PSI converted to a saturated temperature. And our air temperature is 84.5, so we're running up to 85. So we figure we have 99 minus 85, that gives us a TD of 14 degrees. My saturated temperature is 14 degrees over my ambient temperature. The saturated temperature is 14 degrees warmer than the temperature of the air coming into the unit.
Let's look at the saturated temperature a little different way. As the air temperature starts to go up, our head pressure is going to go up, and our saturated temperature is tied directly with our head pressure. So refrigeration systems have approximately a 30-degree TD. Some newer ones have approximately a 20-degree TD. Let's say we have an older walk-in freezer, and it has a 30-degree TD. So let's say that our air entering temperature, the temperature of the air coming into that condenser, is 100 degrees Fahrenheit. That means my saturated temperature would be 30 degrees warmer than that, approximately. So that means my saturated temperature would be approximately 130 degrees Fahrenheit. And I could take that saturated temperature and convert that to a pressure, and that would give you an idea, at least, of what your head pressure would be looking like. So that's a way of using these same numbers and working them backwards. Let's say we have a residential system. That's 2010s. We know it's after 2006, which means it's approximately a 14 SEER system. So we know that our temperature difference, the temperature between the air and the refrigerant, should be about 10 to 15 degrees. So let's say we have a residential unit, 2010 model, my TD should be about 10 to 15 degrees. In other words, my refrigerant should be 10 to 15 degrees above the air temperature. Let's say my air temperature here, the air coming into my condenser, is 100 degrees Fahrenheit. So we're going to write 100 right here, and I would add 10 to 15 degrees. That means my saturated temperature would be 110 to 115 degrees. So that would be what my saturated temperature should be at approximately. So you get this all the time. You're going to be asked, hey, what's your head pressure? Or is your head pressure too high? Or I think your head pressure is too high. How can you know if your head pressure is too high? Well, here's the answer. It's TD. That gives you a good idea. So let's say we have a system that's 2010 model. We need to know our air temperature. Let's say our air temperature is 100 degrees. We know our saturated temperature should be 10 to 15 degrees warmer than the air temperature. So 100 degree a day, my saturated temperature, my liquid saturated temperature should be 110 to 115 degrees. If you wanted to convert that to pressure, use your temperature pressure chart, convert that saturated temperature back into a pressure. And if it's above that, let's say 100 degree day, and I convert that to 115 degree saturated temperature, let's say I'm 120 degree saturated temperature. Well, whatever that converts to in pressure, that 120 degree saturated temperature tells me, I have a high amount of saturated temperature, which means a high head pressure. And then you can start looking at things like airflow, dirty coil, all these things to see what might cause that. But it's a little bit way of working it backwards, but it's much simpler than having a refrigerant number in your mind. Imagine trying to remember every refrigerant out there and also remembering how every refrigerant would act with every temperature. If there was only a simpler way to do that. Oh wait, there is. If we know the SEER rating of the system, we have an idea of what the temperature difference between the air and the refrigerant should be. So no matter what the air temperature does, my saturated temperature should follow. In other words, as my outdoor temperature rises, my saturated temperature will rise and my head pressure will rise. As the ambient or outdoor temperature drops, my TD is going to stay the same, so that means my saturated temperature will drop and my pressure will drop. For example, let's say my air entering temperature was 80 degrees Fahrenheit. So I know my saturated temperature should be approximately 10 to 15 degrees warmer than that. So we'd say 90 to 95 degree saturated temperature. Who cares about the pressure? If my saturated temperature was, say, 100 degrees Fahrenheit, I'd be like, my saturated temperature is too high. My temperature difference between my air and my refrigerant on the outdoor unit is too high. I need to start looking at what might cause that. So looking at condenser TD, understanding what our condenser TD should be and what our condenser TD is a really great way of getting to see what's happening. Now the catch is when you get to this really high efficiency system, it could be down as low as 5 to 13. And when we get variable refrigerant flowing systems with these variable compressors, it's just not applicable because those systems change the compressor pumping ratio all the time. At that point, you just have to go back to the manufacturer specification. But hopefully this will help you. Understanding the temperature difference between the refrigerant and the air is going to be a pretty constant number. And again, at the older systems, you're going to have a bigger change in that number because of efficiencies. But if you understand the temperature relationship between the refrigerant and the air, it makes things a whole lot easier. Understanding as the air temperature goes up, your refrigerant saturated temperature is going to go up as well. And as the air temperature drops, your liquid saturated temperature is going to drop as well. Understanding these things is really important, and that helps make it easier. Understanding TD is easier. That way you can know what a high head pressure is. Because a high head pressure on an 80 degree day is going to be completely different than what a high head pressure would be on a 100 degree day. So hopefully this helps make it easier. Now let's take a look at evaporator TD. Evaporator TD. So we know our refrigerant comes in as a high pressure liquid. We hit our metering device and now it's immediately at saturation, boiling, evaporating, changing state from liquid to vapor. That's latent heat. That's the majority of our evaporator coil. Then we superheat above saturation, which is all sensible, and head back to our compressor. So if we want to find our TD, we need to know our return air temperature. And this is sensible only, so it's going to be the temperature of the air coming into our evaporator coil. That's going to have a big effect on where refrigerant's boiling at. We get our return air temperature and we record that. Then we get our suction pressure. Our suction PSIG, which is worthless. Let's convert that to something important, such as a saturated temperature with a P and PT chart. That's going to be our suction saturated temperature. Remember that saturation temperature is taking place ideally the majority of that evaporator coil. It will be the majority of the evaporator coil with a properly operating TXV, but the fixed surface, it could be a small amount or a huge amount. I mean, who knows? So the TXV tries to maintain that. So if we take our return air temperature minus our suction saturated temperature, That gives us our evaporator TD, temperature difference between the refrigerant and the air temperature. Now this is a catch. That number helps us a lot, but it depends on humidity. Humidity is going to affect that. Latent heat is going to affect that. So this isn't nearly as set of a number as it is with a condensing unit. It has a lot of variance. But typically speaking, residential air conditioning systems designed for an approximate, not set in stone, just an idea of a 35 degree TD, plus or minus 5 degrees, depending on the humidity and airflow. So we just say 35 to give you an idea. I'm going to use 35 in this example. But if we were working in a place that had very high humidity climate, for example, Florida, we may end up using a larger evaporator coil and slowing our blower speed down. By slowing the blower speed down, we'll end up with a larger TD. So I could end up with a 40 degree TD or even a 45 degree TD. And in the other case, maybe I live in Las Vegas, Nevada, and I decide I don't need any latent cooling at all. It's all sensible. I could increase the fan speed and actually make it more efficient. I don't need dehumidification. So by moving more air across the evaporator coil, I'll end up with a smaller TD, say 25 degree TD or even a 30 degree TD, temperature difference between the refrigerant and the air. So that number's not set in stone, but for this example, let's say that we have a 35 degree TD. So let's just run some numbers. Let's just give you an example because this is what I want you to see. Let's say our return air temperature is 80 degrees Fahrenheit, and the system's designed for an approximate 35 degree TD. So if my air temperature is 80, and I subtract my 35 degree TD design, that means my saturated temperature, my suction saturated temperature would be a 45 degree evaporator coil, approximately. So notice that temperature and temperature correlation. So let's see what happened if we were to lower our air temperature. Now let's go back and put our air temperature. Let's say our air temperature is 75 degree air temperature minus our 35 degree temperature difference between the air and the refrigerant. That means my saturated temperature would be at a 40 degree evaporator coil. That's that magical number here everybody using. Well, that's only going to be if we have a 75 degree return air temperature at 50% relative humidity with a set 80 degree outdoor temperature. But it's just to give you an idea. And notice that as we dropped the air temperature down, my saturated temperature also dropped as well. The TD is staying the same. So let's give another example. Let's say we're to drop our air temperature down to 67 degrees Fahrenheit. So return air temperature is 67 degrees Fahrenheit. I'm going to put that in my calculator. And then I want to keep our same design temperature here of 35. So we'll take 67 minus 35 equals our suction saturated temperature of 32 degrees Fahrenheit. That means as the air temperature coming into this evaporator coil dropped, my suction pressure and saturated temperature also dropped. And once we get to 32, it's going to start to freeze. Depending on the amount of moisture in the air, it will start to freeze up. Now there are several things that affect that. That's going to be the humidity, the outdoor temperature, the amount of airflow going across that, the filter, the duct system, if the duct system is perfect, how dirty that evaporator coil. There's a lot of factors going to affect when it starts to freeze. I typically start seeing evaporators starting to freeze at 68, 69 degrees because no duct system is perfect. They're usually restricted. But it just gives you an idea that as the temperature of the air starts to drop, my suction saturated temperature drops. And if my saturated temperature drops, that means your suction pressure is also dropping. And as the air temperature starts to go up, that means my suction saturated temperature is going to go up. And if my suction saturated temperature goes up, my suction pressure goes up as well. Because the air temperature is changing, your suction pressure is also going to be changing because of this beautiful thing we call TD, temperature difference. Temperature difference between the refrigerant and the air. Remember that refrigerant needs to be a lower temperature than the air to absorb heat. And typically speaking, residential systems design a 35 degree temperature difference. All right, now we understand residential evaporators. Let's take a look at commercial evaporators. Here we have our liquid line coming into our metering device, and it's usually a TXV, and the metering device restricts it from a high pressure liquid to a low pressure saturated mixture, which means most of that evaporator coil, the refrigerant's boiling from a liquid to vapor, and that last little bit superheats all the way back to the compressor. So the return air temperature, the air coming into that evaporator, is going to have a dramatic effect on their suction pressure. So the temperature difference is the temperature difference between the suction saturated temperature and the air temperature. If I know my return air temperature with a thermometer, I put that temperature in right here, minus my PSIG converted to a saturated temperature, and I put that number here, Return air temperature minus my suction saturated temperature equals my evaporator TD, temperature difference. Now typically, this is typical for evaporator coolers, walk-in coolers, walk-in freezers, is approximately a 10-degree difference. In other words, the saturated temperature, the PSIG converted temperature, the saturated temperature is approximately 10 degrees lower than the air temperature. In a walk-in cooler, it's a lot more constant because your airflow is the same. Walk-in coolers don't have a varying amount of airflow. They just move a steady amount of air. They also don't do a lot for dehumidification, so it's mainly sensible cooling, which is a lot easier to work with. So in a walk-in cooler, let's say our return air temperature is at 35 degrees Fahrenheit. So we put a thermometer, the air coming in, and right here we're at 35 degrees Fahrenheit. We know that our saturated temperature is going to be about 10 degrees less than the air temperature. So 35 minus 10 gives us our suction saturated temperature of about 25 degrees Fahrenheit. So 25 degrees Fahrenheit, notice that will freeze. But these evaporator fins are built spaced out very well. They're a lot farther apart than residential. And these fans stay on all the time. So when the system cycles off, the fans stay on and it causes that 35 degree air over this 32 degree ice and it melts the ice back down. We call that off-cycle defrost. So it's okay that our suction saturated is below 32. They've designed it. Let's take a look at a walk-in freezer. Walk-in freezer, let's say we design that freezer to be operating at 0 degrees Fahrenheit. It means the temperature of our air coming into the evaporator coil is 0 degrees Fahrenheit. So 0 degrees minus 10 degrees gives us a negative 10 degrees saturated temperature. Negative 10 degrees saturated temperature, that's awesome. Now the difference is when this system cycles off, I'm still going to be at 0 degrees air coming across here, so it's still going to be frozen. So that's why walk-in freezers have a defrost cycle. In other words, they shut the fans off, they use little heaters, and they start melting the ice off of here manually. A lot more goes into that. It's just giving you an idea of how we handle the ice situation. Now what's important to know about that is the air temperature is going to affect that suction saturated temperature and also the suction pressure. So let's say we're working on a walk-in cooler, which is typical. We're going to have to go fix them. So we're working on a walk-in cooler and our air temperature is say at 50 degrees. They have a lot of products in, the unit's been down, we just got it back up and running and it's at 50 degrees. So as we're seeing that, we see, wow, my suction pressure is really high. Or is it? So our return air temperature is 50 degrees. We subtract 10 degrees from that. That means my suction saturated temperature will be about 40 degrees Fahrenheit. So that might typically seem high, but it's a 10 degree temperature difference. That's what it's designed to maintain. So as the air temperature of your box over here starts to drop, that means my suction saturated will drop and my suction pressure will drop also, because they are interconnected. I have one of my students, he graduated, started working for a company. He said, make sure that all of your box temperatures are exactly at 35 degrees. And I was like, well, that sounds great and all, but you're going to have varying pressures and varying saturated temperatures with air temperature. So the air temperature is huge. It's a very important part of this. Now, on a key note, it's important that anytime you're working at the walk-in cooler or a walk-in freezer is to wait there with it, babysit it for the temperature to come down to set point. You want it to cycle off naturally. So if I have a walk-in cooler and it's set for 35 degrees, I want to sit there and wait for that cooler to get to 35, or maybe it's set for 38. It definitely should be below 40, but it's whatever it's set for, I'm going to wait for it to cycle off. And that may be very time consuming. We'll do some other paperwork, listen to a podcast, do some studying, but I want to make sure that temperature actually gets there. Now, when that temperature is about to cycle off, then my suction saturated should be right on the money. I should be, let's say I'm at 35 degrees, 35 minus 10, I should be right at 25 degrees suction saturated. And whatever you convert that to the pressure will be your quote unquote correct pressure. But that TD gives us a lot better thing to work with, a lot more precise thing to work with. It's also important to note if you have a thermostatic expansion valve with a walk-in cooler, it's close to set point, that's where you want to actually check your TXV. You want to see if it's doing the superheat that it should while it's there at set point or very close to set point.